Today's manufacturing and operating processes are constantly improving in efficiency and safety. The gains are a result of optimization from studying things like human-machine interaction, process variation, and capital equipment utilization. These improvements rely on operational data that can be used as the basis for decision making. The data needs to be accurate, and the methods for acquiring the data should minimize cost and disruption. In this video, we'll take a look at a method for using computer vision tools to track and construct an operational history for a process. Hello. The basic approach that we'll take is to combine information from an object detector and a motion detector. So with the object detector, we can determine whether a person or a tool is within the field of view. And with the motion detector, we can tell whether that object is active or not. In this first video, I'd like to walk you through some of these tools and give you a feel for how they work. And in the subsequent videos, we'll apply it to an industrial process and extract an operational history. So let's get started. Some of the challenges that we face with object detection and classification comes from the need to account for different perspectives, variations of an object, and lighting conditions and backgrounds. The images that you see here are from an internet competition that was run by Kaggle.com back in 2014. The challenge was to correctly classify images of cats and dogs. So these images were picked directly from their test set. So here our object classifier needs to be able to recognize different breeds and deal with partial occlusion by things like the kennel fencing and slats on the wood fence, or by the can of dog food. So despite these difficulties, it's very impressive to see that the top competitors were able to achieve 98% accuracies. These best performing object classifiers are typically based on a convolution algorithm. The basic strategy with the convolution image recognition algorithm is to condense the complex image features down into a collection of convolved basic feature representations. Then we can use a classifier to interpret what combinations of the basic features can define an object. To make this a bit easier to understand, I'll walk you through a quick example that demonstrates the concept on an image of a letter. We start with a binary image of the letter P in two feature kernels, a vertical line and a diagonal line. We'll convolve the image with the feature kernel to create the convolved output, which we'll show in the orange block. The convolution is performed with element-wise multiplication of each cell in the convolution window, and then summing them up to get a single value. So as we walk through this simple example, be thinking back to our cats and dogs images, where their features might be represented by these simple line kernels, but maybe also something a little bit more complex and at different scales, with things that might look something like an eye or a nose or an ear. So let's start by placing the convolution window for our vertical line kernel in the upper left-hand corner of our image. We multiply and sum the cells together and we get a value of 3. So then we move the convolution window and repeat. And then we repeat again for the diagonal line kernel. And then we're done. So let's take a different letter, the letter Z this time, and repeat the process. So now we have the convolution outputs for each letter. The next step is to feed these convolved features into a classifier that can interpret and predict the letter. The classifier first needs to be trained by feeding it a series of images so it knows how to associate the convolved features with each letter. There's some complexity to integrating the convolution algorithm in the classifier that we won't discuss, but I hope this gives you a feel for what's under the hood. So in an industrial process, we're often interested in detecting multiple instances of an object, for things like tools or if there's multiple parts in an assembly. Now, one approach you might think of is we could just simply take our classifier and train it on images that contain multiple instances. Well, this starts to run into problems if we have a system that has a great number of objects. There we would have to train our classifier on every possible combination of the objects and number of instances that we might expect. So it turns out the better approach is to simply take our image, break it down into subregions, and then we can look in each of those subregions for the object. And this turns out to be much more computationally efficient and is very effective in detecting multiple instances of objects. The image you see here is a frame from the drill rig videos we'll analyze later. On the left is an example of an image extracted from the video, and on the right is the same image, but it's overlain with a blue grid that contains approximately 2,000 grid proposal regions within the larger image. And then the colored regions are the grid proposals where the classifier has detected objects. In the processing pipeline, the program systematically assigned region proposal rectangles in a grid over the image. We then filter back the number of region proposals by constraining the region geometry with things like minimum or maximum size or aspect ratio. Then the object detector looks at each region proposal sequentially and then returns regions where it finds objects that it recognizes. It then combines any overlapping object detection regions using a method called non-maxima suppression and then creates the final output. So this sounds like a lot of processing steps, and you're probably asking yourself about how long all this takes. Let's go through the example of the drill rig videos that we'll analyze later. So there we start with the HD video image that's 1920 by 1080. We first resize it down to 1000 by 1000 pixels. Then we apply our grid engine, which creates about 100,000 region proposals. Then our geometry filter reduces that down to about 1400 regions. Then the convolutional neural network analyzes each region, returns the object classifications, and then we combine any overlapping detections. So those are the main processing steps, plus we have our background detector that we'll discuss next that's running in this loop. But all that takes about a half a second on the GPU. So this method should work reasonably well for real-time analysis on processes that are about a second or slower. For faster processes, we can still use this method, but we would not be able to apply it in real time. So let's turn our attention to the foreground background detector. We can start with the assumption that if we have a pixel value that's changing with time, then it's part of the foreground, but if it's static, then it's a background pixel. And we can implement this by taking the first few frames of our video and using it to define the background values that we can compare with each new frame that we acquire. And this approach should work pretty well as long as we don't have any changes in lighting and we get a good clean shot of the background when we start. Well, it turns out that there's a better approach, and that's if we can take a Gaussian function and we fit it to the recent time history of the pixel value. We acquire a new pixel value, compare it to its time history, and if it varies more than a couple standard deviations, then we can assign that as being foreground. And this approach has a lot of advantages. One is that we don't need to worry about acquiring a clean background image to start with. And also it's adaptive, so it can accommodate changes in lighting as we go along. So here's a quick demonstration of the two techniques that we just discussed. I think it's safe to say that OpenCV is not going to be asking me to work on their foreground background detectors anytime soon, but hopefully this highlights the advantages of that second approach. Well, this brings us to the end of the video. In the next two videos, we're going to be applying these two techniques and use it to extract an operational history from a drill rig pipe change. I hope you found this interesting, and if you felt it was useful, please leave a like or a comment. We'll see you in the next video. And thanks for watching.